You know, when you look up at the night sky, everything seems so permanent, so unchanging. But that glowing sphere, we all know, the moon, well, it's actually in the middle of a very, very slow motion breakup with Earth. So today, we're going to dive into the quiet, cosmic forces that are pushing our only natural satellite away from us, inch by tiny inch.
But before we get into the how, let's just do a little thought experiment. I mean, what if you woke up tomorrow and the moon was just gone, vanished? Sure, the nights would be incredibly dark, amazing for stargazing, right? But pretty soon you'd start to realize just how connected our world is to that missing piece of the sky.
Because here's the thing, the moon is leaving. It's not a hypothetical, it's happening right now. It's drifting away from Earth by this much every single year. That's about the same speed your fingernails grow. And yeah, it sounds like nothing, but you stretch that out over millions or billions of years, well, it changes absolutely everything.
And look, this isn't just some wild theory. It's a hard measurement. Scientists can literally fire powerful lasers from Earth, bounce them off these special mirrors that the Apollo astronauts and Soviet rovers left on the moon, and time the return trip. The precision is just incredible, down to the centimeter. That's how we know for a fact it's getting further away.
So what's causing this? What's the engine driving this cosmic separation? Well, the answer isn't some mystery force from deep space. It's right here in our own oceans. It all comes down to the tides.
So how does this even work? It all starts with gravity, but it's a little more complex than you might think. See, the moon's pull isn't the same across the whole planet. It pulls just a little bit harder on the side of Earth closest to it and a little weaker on the side that's farthest away. This difference creates a kind of stretching effect, a tidal force, that actually deforms our entire planet. Okay, so that stretching force pulls our oceans into two big bulges, one facing the moon and another on the exact opposite side of the planet. But here's the kicker. The Earth spins way, way faster than the moon orbits around us. So our planet's rotation actually drags those big water bulges slightly ahead of the moon. And now you've got this huge mass of water with its own gravity, pulling the moon forward, giving it this tiny little energy boost. It's like hitting the gas pedal in orbit. It slingshots the moon into a slightly higher and therefore more distant path.
But of course, that energy has to come from somewhere, right? Physics 101, you can't create energy from nothing. That little boost the moon gets, it's literally stolen from the Earth's rotation. As the moon speeds up and moves away, the Earth's spin slows down, just a tiny, tiny bit. In fact, our days are getting longer by about 2 milliseconds every century.
And this whole dance is nothing new. It's been going on for billions of years. And believe it or not, we can actually see the evidence of it in our planet's deep, deep history.
So how on earth do we know that? Well, paleontologists have found the proof in fossilized clam shells from the age of the dinosaurs. Like tree rings, these shells have daily growth rings, and by counting them, they figured out that 70 million years ago, a day on Earth was only 23.5 hours long. The reason? The moon was much, much closer, so the Earth was spinning faster.
This is where it gets so cool. The physical proof we find in the fossil record lines up perfectly with what our astronomical models predict. You've got two totally different fields of science, geology and astronomy, telling the exact same story. The moon used to be closer, and our days used to be shorter. Period.
All right, so we've looked at the past. Now, let's hit the fast forward button. What happens as the moon keeps drifting away? What does a world with a really distant moon, or maybe no moon at all, actually look like?
Well, the very first thing that would change is the engine that's causing all this in the first place, our tides. Without the moon's gravity being the main player, our ocean tides would shrink by about 75%. The sun still has some pull, sure, but it's nothing compared to the moon. The whole rhythm of the oceans would just fade.
And that would be an absolute ecological nightmare. I mean, think of all the creatures, crabs, mussels, snails, that live in those intertidal zones. Their entire existence depends on that daily cycle of water coming in and going out. If that goes away, their populations collapse. And that collapse ripples all the way up the food chain. It would be devastating.
But the loss of tides? That's just the beginning. The moon's influence goes way deeper than just our oceans. It acts as a massive stabilizing force for the whole planet. So what happens to our global climate when that stabilizer is gone?
This is probably the wildest consequence of all. Right now, Earth is tilted on its axis at a nice, stable 23.5 degrees. That's what gives us our regular, predictable seasons, and we can thank the moon for that. Its gravity acts like a giant gyroscope, keeping us steady. Without that gravitational anchor, scientists predict Earth's axis would start to wobble chaotically, maybe swinging anywhere from 10 all the way to 45 degrees.
A wobble like that would create total chaos for our climate. Seasons, as we know them, would just cease to exist. They'd be replaced by these wild, unpredictable swings in weather. I mean, to put that in perspective, we think past ice ages were triggered by shifts of just 1 or 2 degrees. Can you imagine a 20 or 30-degree swing? It's almost unthinkable. So the moon is leaving, and the results would be, well, pretty catastrophic. But does that mean it will eventually break free entirely? Will it just drift off into space? To answer that, we have to look at an even bigger timeline, the cosmic one.
Okay, so there are basically 2 cosmic clocks ticking here. On one side, you have the moon's retreat. If nothing else changed, in about 50 billion years, Earth's rotation would slow down enough to be tidally locked with the moon, meaning the same side of Earth would always face it. At that point, the drift would stop. But look at the other clock. In just 5 to 7 billion years, our sun is going to run out of hydrogen and swell up into a red giant.
So the verdict is pretty clear. The sun's clock is ticking way, way faster. Long before the Earth and Moon can finish their slowdowns, the sun is going to expand. Its intense heat will boil our oceans away, which gets rid of the very tides pushing the moon away in the first place. And its outer layers will most likely just completely swallow and destroy both the Earth and the moon.
So no, the moon will never truly escape. But this whole journey, this slow departure, really lets us step back and see just how vital it is for us. Let's just do a quick recap of everything our world would lose if our companions suddenly vanished.
Man, it's a pretty stark list. Tides fade away, coastal ecosystems collapse, the climate goes haywire as the planet wobbles like a top. We'd even lose a gravitational shield that helps protect us from some asteroids. Basically, without the moon, Earth becomes a much more chaotic, unstable, and dangerous place to live.
It really puts it all into perspective, you know? This quote here just nails it. The moon isn't just some pretty light in the sky. It's an active, essential partner in the delicate balancing act that allows life to thrive here. It's our stabilizer, our protector, and our ancient timekeeper, all rolled into one.
So, while we don't need to worry about the moon vanishing tomorrow, its slow, patient retreat is just this powerful reminder. Nothing in the universe is really static. Even the things that seem the most permanent are all just part of this grand, incredible, and constantly changing cosmic story.
It really makes you wonder, doesn't it? The moon is leaving us, centimeter by centimeter. What other massive, profound changes are happening right now, on timescales that are just too vast for us to even notice? What's the next big chapter in our planet's cosmic story?